Hello again. In this video, we're going to look at the Gram-Schmidt process for three vectors to construct an orthogonal basis. And let's do this with the following example, where x1 is 1, 1, 1, 1, x2 is 0, 1, 1, 1, and x3 is 0, 0, 1, 1. You can see that x1, x2, x3 is linearly independent, and thus a basis for a subspace W of R4. And you can see that because x1 cannot be written in terms of a linear combination of x2, x3. You have two zeros here, and how are you ever going to get that 1? Or you can show this. You can show that C1 vector x1 plus C2 vector x2 plus C3 vector x3 has only the trivial solution, i.e. where C1, C2, and C3 all equal 0. So I'm just going to take this is the same as the matrix AX equals 0. This is actually the 0 vector this time. And I'm just going to rearrange my rows. I'm going to switch these up. So the row 1 is I'm going to interchange actually 2 and 1 and 3. And then I'm going to switch again 2 and 3. So that way it has a few steps as possible. And so then I'm going to get all zeros underneath this first one here. Multiplying -1 times row 1, adding to row 2, we get 0, -1, -1, and 0. Take -1 times row 1, add it to row 3, you get 0, 0, -1, 0. And then take -1 times row 1, add it to row 4. Let me give myself a little more room. You get a row of zeros, 0, 0, 0, 0. So you can clearly see, if this is C1, C2, and C3, that C3 is 0. Then plugging in C3 is 0 into the second equation, you would get C2 equals 0. And then plugging in C2 and C3, you get C1 is 0. So if you didn't see it, you can see that these three vectors are linearly independent. So what we're going to do is we're going to construct an orthogonal basis for W. So we're just going to let V1 equal x1. And you can see that the span of x1 is going to be the span of V1 since they're the same vector. And we're going to call that W1. So V1 is the vector 1, 1, 1, 1. So now V2. V2 we know is x2 minus the projection, which is what this is, of V1 onto the subspace W1. So it's x2 dotted with V1 over V1 dotted with itself. Figuring that out, we get x2 minus, so if I take x2, which is right here, this is x2, dotted with V1, which is just x1, we get 3. And then V1 dotted with itself, which is the same as x1, so we have 4. Putting in x1 and V1, we get, x2 and V1, and again, V1 is just x1. There's V1. So this becomes -3/4. This one would be 1/4, 1/4, and 1/4. So now we just created an orthogonal basis V1 and V2 for what we can call W2. And we know the span of x1, x2 now is going to be the same as the span of V1 and V2. Before we do the next step, step 3, where we find V3, I'm going to scale V2. By multiplying V2 by 4, I'm going to call it V2 prime. You don't have to do this, but if you don't feel like dealing with fractions, it's still going to be an orthogonal basis. Since V1 is 1, 1, 1, 1, V1 dotted with V1 prime, you can see is -3 plus 1 plus 1 plus 1 is 0. So V1 and V1 prime are orthogonal. So now let's find V3. V3 is going to be x3 minus the projection of x3 onto V1 and also subtracting the projection of x3 onto V2 prime now. So here's the projection of x3 onto V1, and here's the projection of x3 onto V2 prime. So we're going to take that projection times V1, and then we're going to take this projection times V2. So let's go figure all that out. Since x3 is 0, 0, 1, 1, from the top of the page there, we have x3 dotted with V1, which is 1 plus 1, we have 2, and V1 dotted with itself is 4. Doing the same thing with V1 prime. So x3 dotted with, V2 prime is going to be this and these two. So we have that V2 prime dotted with x3 is 2 again, and then V2 prime dotted with itself is, we have 9 plus 3 is 12. There it is. That is V3. So plugging in those vectors, we get x3 minus 1/2 of V1 minus 1/6 of V2 prime. And that becomes, multiplying in the negative 1/2 and the negative 1/6 and adding them together, you get this vector right here, which reduces to 0, negative 2/3, 1/3, 1/3. That is V3. And you have that, therefore, V1, V2, we'll call it prime, and V3 is an orthogonal set. And we know, therefore, it's an orthogonal basis for W, where W is equal to the span of x1, x2, x3, and now we know it's also the span of that orthogonal set. Here's a picture of the V1 and V2 prime on a plane W2, because if you remember, W2 was the span of x1, x2, or the span of V1, V2. You can see that there. And so what this V3 is going to be is we're going to take x3 and we're subtracting off both of those projections, right? This together is the projection of x3 onto W2, onto that plane. In other words, the projection, I wrote it here, the projection of W2 of x3 is this term, the projection of x3 onto V1, and the projection of x3 on added to the projection of x3 onto V2. And I forgot my V1 right here, and this should be a prime, V2 prime. There it is. So that means that we're going to subtract that whole quantity. So looking at this visually, we're going to look at the plane W2, and the projection of x3 onto W3 is this orange line here. So when we find V3, you can see we're taking x3 and we're subtracting off. All this is the projection of x3 onto W2. Subtracting off that projection, you get the dotted line, which is orthogonal to both of those, which is V3. You can also look at it by x3 added to the opposite, which is right there. So you can see the blue line would be the V3. So that is the construction of V3 from x3 and W2, which again, W2 is the span of x1 and x2, or V1 and V2. That is it. Hope that helps.